A very good morning, good afternoon. Today, on behalf of the Board of Urban Environment, also known as BUE, I invite you to the first webinar organized by the BUE members. The BUE mission includes, within its interests, the interactions of the natural and built environment with the atmosphere, considering cities as agents of global change, assesses urban environmental implications for engineering designs, planning, and policy, conducts weather forecasting for urban areas and city dwellers, and many other functions of urban climate and related fields. BUE also encourages transdisciplinary actions between scientists, private companies, and public actors in order to advance the development of integrated urban climate services and to raise awareness of urban climate in order to improve the potential future policy implications about city management and planning. Now, this was in a nutshell what BUE, the mission of BUE is, which most of you must be aware, and if you're not aware, it's one of the boards of the American Meteorological Society. And as the chair of BUE, I would like to thank Van Duan to lead this effort, and all other BUE members for helping with the planning and organization of the webinar. We will have our second webinar in February 2021, right after the AMS annual meeting. Please look out for notifications from BUE on the AMS webpage. And so with no further delay, I will hand it over to Van to introduce our esteemed speaker for today's webinar. Thank you for listening.
Thank you, Chana, for your nice introduction about the Board of Urban Environment. A very warm welcome you all again. My name is Van Duan. I am an assistant professor from the University of Tsukuba, Japan. It's my great pleasure to be the coordinator of this first webinar hosted by BUE. Let me introduce today's speaker, Professor Janet Barlow. Janet Barlow is a professor of environmental physics at the University of Reading, UK. She is the winner of the 2019 Luke Howard Award for outstanding contribution to the field of urban climatology. She has undertaken innovative research and author of many groundbreaking and influential publications addressing a broad range of topics such as urban boundary layer, wind energy, building ventilation, and indoor climate. Thanks, Janet, for accepting our invitation to share your knowledge with our AMS citizens. Just before starting up, just a few housekeeping items to mention here. If you have any question during the presentation, please type them in the chat box in your control panel. Janet and myself will go through your question after presentation. So now it is time to hand it over to Janet to begin the talk. Janet, or you're now.
Thank you very much for those kind words of introduction, and thanks very much to AMS BUE for asking me to give this talk. I'm delighted to do it, even though it would be much nicer to be with you all in person, of course. So before I start, I just want to quickly say thank you to the people named on the front slide who've provided technical support to some of the experiments, which I'm going to show you in the following slides. Okay, next slide. So we see increasing awareness of the quality of air that we breathe. Certainly in urban areas, we know that cities are very polluted. They're polluted at the scale of the city and the streets where the traffic is emitting the pollution. And we're aware that in our buildings, we have indoor air quality issues which are starting to come up the agenda. Now, in this particular year with COVID, we are very much starting to talk more about ventilation. So good ventilation of buildings. So how do we exchange stale, polluted, perhaps pathogen-laden air inside our buildings with fresher air outside? And how can we do that effectively? But then we have to think that the air we're taking into our windows comes from the streets outside. Good ventilation depends on having clean air at street level, and the air in the street is influenced by the quality of air at city level. So all these processes are connected to determine what the quality of air is in the buildings in which we live. And not just air quality, an increasing concern is temperature. So are our buildings overheating, and will they overheat in the future? And so ventilating buildings and cities effectively is something we need to think about design issues in cities to achieve. Next slide. So what I want to do today is to consider the questions of how we make our cities breathe more easily. Next. I'm going to structure the talk today into 4 sections. So initially, an initial quick overview of urban wind climate processes at different scales, then to go through ventilation at the scale of the building, street and neighborhood, and the urban boundary there. Okay, next. Okay, so starting with the processes, we can think about that. Yes, please, next. We can think about the processes of wind flow around our individual buildings, where we might be sitting watching this talk. And we know that the flow is very 3-dimensional. It's very much determined by the shape of the street and the building itself. We know this 3-dimensionality of the flow is what we find in the roughness sublayer. Right? So this is the bottom layer of the atmosphere, above which we find the inertial sublayer, where the flow is a lot more homogeneous. It's the same everywhere. And the depth of the roughness sublayer is around about 2 to 5 building heights, which we give the symbol H. And the scale of the street is around about 10 to 100 meters. Next. So if we zoom out a little bit, that street is sitting in a neighborhood of similar buildings, which might have a scale of around 100 to 1,000 meters. So that's a patch of the city, which is very similar. It has a similar friction that it exerts on the wind above. And as the flow is coming across the city from left to right, then an internal boundary layer is formed. So this is an area where the wind flow is in equilibrium with the surface. And then when the wind moves on to another patch, it has to develop a new equilibrium determined by the roughness. So these internal boundary layers at a certain height, they blend out, and we get back to some kind of homogeneous wind field again. So if we move on to the next slide. Then we zoom out again to the city scale. So if the city is around about of the order of tens of kilometers in size, we see the rural air flowing over the patchwork of the city surface. There's a gradual adjustment over each patch, but then we build up an entire urban boundary layer which is adapted to the whole city. And because the city is hot, there's convection over the city which mixes up the air from the surface up to the air above in the so-called mixed layer. Next slide. If we zoom out again, the next scale up is that our city might be sitting in a regional context which determines the wind climate. So if the city is surrounded by hills, we might have these kind of processes occurring. So at night time, the picture on the left, where we have cold air sinking down off the mountains, which might be flowing into the city, that might provide cool air, but it might also help to trap pollutants at low level by making it stable. So by daytime, the process reverses and hot air is drawn up the slopes of the hills. And this again can provide flows out of the city of air. So we have to think about any flows induced by mountainous or hilly terrain. Next. Our city might be on the coastline. It might be next to a big body of water, like a lake. And this can cause a different kind of flow. So if your land surface is warmer than the water, then hot air will rise over the land surface, and that will pull in cold air from the body of water. And this causes a sea breeze circulation. So cold air coming in at the low levels, and then air returning at high levels to create a circulation. Next. So some model studies have suggested that greater urbanization next to the sea can actually enhance the circulation. So you can imagine this would happen because the city is a lot warmer than the land if it weren't there. And next, this makes hot air rise more strongly. And next, this will pull air, cold air off the sea. So cities can actually change the wind climate in a beneficial way if in certain circumstances. Next. So I mean, a city can have a lot of benefits from having sea breeze kind of ventilation, but only if we don't obstruct that flow by poor urban design. So these buildings are clearly of slowing down the flow that's coming off the sea. Next. And these kind of ideas of harnessing regional flows for the better is behind the so-called urban ventilation corridor idea. So if you look at the picture on the right, we have a city which has got very good sea breeze potential. And if you look at the picture on the left, zooming in, we can harness the sea breezes and redistribute them through the city via some kind of pathways that have been designed in using good planning techniques. So this is a really good example of the way that the regional scale weather, the regional scale wind climate can be harnessed and benefit the neighborhood scale wind climate within the city. Next. So that was giving you an overview of all the processes and starting to think a little bit about how they're linked to, these different scales are linked. But now I want to zoom in back to our building and think about ventilation processes just at the scale of the building. Next. So I'm not aware of what disciplines we have in the audience, but just to give a definition of what typical building ventilation systems we have. We can have natural ventilation where we simply open the windows or slats or shutters to let air pass through the building. We can have mechanical ventilation, which using a little bit of energy to drive pumps or aircon systems to give a constant flow rate through the building. Or we can have, like in this picture, mixed mode operation with a mixture of the two that can provide building ventilation. I want to focus on natural ventilation as a process in the next few slides, because this is where we're most sensitive to what the wind climate is outside of the building. Next. So how does natural ventilation occur? So what we have, if we have some kind of wind profile given by the graph on the left-hand side, an increase in wind speed with height, when that wind hits the building, if we look to the right-hand side, the top diagram shows us that the wind causes a high pressure region where it meets the front of the building, and around the back of the building there'll be a negative pressure region, and it's that difference in pressure which drives flow through the building from the positive to the negative pressure region. Now that's if the wind is blowing, the pattern can look like that. If the wind is very weak, then we have this situation down in the bottom where it's a temperature driven effect. So the hot temperature inside the building causes hot air to rise, and then that sucks in cool air into the building, just a little like that sea breeze circulation. It's a pressure driven effect. But if you, can you click next? The question for urban planners and engineers designing ventilation systems in buildings is what's going to happen when you surround your building with other buildings? Next. Next. Okay, video's not going to work. Never mind. So we know that the flow around buildings is very turbulent and very unsteady. So a basic question we wanted to ask was, how is the ventilation of a building changed by the presence of other buildings? Next. So we, with a group of colleagues, we started something called the Refresh Project a few years ago to look at the natural ventilation of buildings, looking at the processes that were controlling the ventilation. Our motivations were that we spend up to 90% of our time is spent indoors, and this year more, probably more than that. in the UK, the context is that we rely very heavily on natural ventilation of our buildings. We don't yet have extensive air conditioning. So we want to make it work as much as possible because it's a sustainable option. Work hours as well will be lost due to overheating of cities under climate change. So this is a concern of some of the city authorities in particular. So we were curious as to how well we could model natural ventilation of buildings. How well can we predict natural ventilation? So instead of starting with a really complicated city like you see in the bottom left-hand picture, we wanted to simplify things. Next. And the way we did this was to build our own mini city that was very much a simplification of what a city neighbourhood would be like. The Silsoe city. So Silsoe is a place in the UK where wind engineers have been doing experiments around buildings for some time. And the blue cube that you can see is a test building. So you can put windows in it, front and back, but also it's instrumented. So it's got many measurements of pressure all around the outside of the building, which is the key variable you need to measure to determine ventilation. If you want more information about it, you can look at Richard's 2012 as an example paper. So the experiment we did, we added in lots of other measurements, including a reference wind speed measurement, which you can see to the top of the slide, and other measurements around the building itself. Next. And the other thing you can do, of course, when you're not in the middle of a city is you can do things like smoke visualization. So we can really see how the buildings themselves are creating large lateral fluctuations, which is clearly going to influence the sort of ventilating pressure on the skin of the building. Next. Okay, this is a slightly busy slide, but I'll take you through it. So our basic question was, how much does the building array reduce the ventilation rate? So if you see the blue cube, what we had was at the front and the back of the cube, we had windows, and we measured the pressure difference between the front and back of the cube. That pressure difference, delta P, if you look at the equation on the left, Q equals A, EF, etc. You can see delta P is the pressure drop across the building, and the ventilation rate Q is proportional to the square root of that pressure drop. Now, ventilation rate will increase as we increase the wind speed. So if we go to the other equation, Qn is the normalized ventilation rate. So what we're doing there is taking the ventilation rate Q and dividing it by the reference wind speed Uref and the area of the window. So we get a sort of standardized ventilation rate. What the graph is showing you below is the result of two sets of experiments. One where the cube was isolated in blue, just on its own, and the pink dots are for where it was surrounded by the array of buildings. So we're interested in the difference between the two. And what we did was to look at the ventilation rate as a function of wind direction, theta ref, which is on the x-axis, and 0 is where we have winds coming from the front of the array, so coming from the top of the slide, if you can imagine that. Next. So can we go back? So what we see is that there's a reduction of around about 75% in the ventilation rate, the blue points down to the pink, for the direction of 0 degrees. So this is the maximum reduction in ventilation we see where the building is the most blocked by the array of buildings. However, if we imagine flow coming from the 90-degree angle, which is following along the streets, if you like, and is parallel to the windows, then there is very little difference between the two situations. So the array is not having very much of an effect at all when we have a 90-degree direction. So there's some subtlety in terms of the impact of an array on the ventilation of a single building. Next. Was also done on this project by my colleague Marco Felipe King at Leeds. He did some LES simulations, which was coupling the indoor flow inside the building and the external flow. This is quite technically difficult to do, and he compared it with the results that we got for the field experiment. But these show quite nicely how the external flow around the building affects the internal flow of the building itself. So if you look at the top right-hand picture, we have the flow around the building. Warmer colors means faster wind speeds. and the flow is coming from the bottom of the page now. You can see inside there's a jet of fast flowing air which connects those two windows. And even if the picture on the left is showing a slightly different wind angle, you can still see that connection of the flow between the front and back, which provides effective cross ventilation as it crosses the room. If you look at the bottom right, then you can see the effect of the array on the wind field. That what I want to draw your attention to is inside that same building in blue, that jet has disappeared. So the external flow has disrupted the internal flow of the building. And then when we look at the bottom left-hand picture where the flow is coming from a different angle, we can still see that that jet has disappeared. But we can see these rivers of fast-flowing air moving through the array, which shows us for very slight wind angle changes, we can get an improved ventilation of the street network, which shows it's very non-linear. The details matter here. But this was a very interesting finding as to how external flow is impacting on the internal flow. Next. So that was just one example of thinking about building ventilation and how it is affected by street flow. I want to go up the scales now and think about how a neighbourhood can be better ventilated by different shapes and layouts of buildings. Next. So this is a bit of a classic diagram, street canyon flow, where we have two parallel streets. And the key thing here is that the wake of the upstream building gradually starts to interfere with the downstream building, and gradually, as the buildings get even narrower, it fills the entire street. Next. So we can divide these different flow regimes into isolated roughness, wake interference, and skimming flow. And this is dependent on the aspect ratio of the street. Next. Yeah, can you try next and see if these videos work? If they don't, they don't. Apologies, we've had some technical, no, all right, okay. So what we were interested in, the piece of work that we did was to compare, was to ask, well, what does the shape of the roof make? Does that make a difference to the kind of flow that we see in street canyons? So we did some, thanks to Brent Leifel at the Uni of Hamburg, we did some flow visualization for two different street canyons. The one on the top left, where we have an aspect ratio of 1, it should be skimming flow. We see flow arrows coming from right to left in yellow. We can see the recirculation in the street. We released some smoke at the bottom of the street so we could actually visualize how much was escaping to the air above. When you look at the bottom right-hand corner, there's a pitched roof on the buildings. The scene looks a lot smokier, and what happens is that by adding a pitched roof to the buildings but keeping the same aspect ratio, you actually reduce the flux of pollutant out to the air above by around about 40%. So those details in the design of the roof shape can really make a difference to the ventilation of the street. Next. Okay, so we're getting a picture of street canyon flow that's relatively straightforward. If you look at the top left, we can see if you look at the perpendicular picture, we have a recirculation, we have a little bit of a shear layer at the top of that. When we look at the top right, when we're looking down on the top of the street, we can see there is channeling along the street. And the bottom figure is showing how you combine both of those when you have flow which is at an oblique angle to the street. There's a kind of helical flow, a sort of vortex sort of stretching down the whole of the street. That we've got a pretty good handle on in terms of conceptually understanding. Next. But if we look at street intersections, then the flow is a lot more complicated. So this is a diagram from based on experiments that we did in London. We were based around a particular street intersection, and we were thinking about the flow pattern for oblique directions. So the flow is at an angle to the intersection, and this is kind of what it looks like. So this is based on wind tunnel experiments, field experiments, and simulations to draw it all together. The flow from a side street can be lifted up at the intersection, so there's sort of vertical displacement of the air, and the flow, if there is a wider street, main street, then the flow down the main street is dominant. So at intersections, there's really complex sort of flows which are determining ventilation, and I'm not sure we've got a very good general picture of what's going on at intersections at the moment. Next. So the final aspect we were thinking of was, what about the height of the buildings? If we have a neighborhood with heights, the buildings have a uniform height, what happens if we start to vary the height of the buildings and make it non-uniform? And this is we did some wind tunnel experiments releasing a scalar at street level, which simulates pollutants. And it's based on a geometry used previously by Cheng and Castro and Zi et al. Next. So what we see on the left is the concentration field for the uniform height buildings, and on the right it's for the non-uniform. And what you're looking at is you've got a bird's eye view of the concentration field at 0.3 H. So this is about a third of the way up the buildings, very much sort of in the breathing zone. And you can see the warmer colors are higher concentrations, and naturally there's a higher concentration in the wake of each building, as you might expect. But if you look on the right-hand side, there's a bit more variability in that picture. And if I can draw your attention to, there's a building labeled 17.2, where the concentrations are a lot more blue. So the air is a lot cleaner directly around this tall building. This is the tallest building in the array. Bear in mind, it's not even twice the mean building height. It's just taller than the other buildings around it. The flow around the building is much more intense, and it seems to be scooping up the pollution from street level and taking it away somewhere. So let's see on the next slide where it's gone. So on the left-hand side, what you're looking at is the concentration field at 1.2 times the building height, so just above roof height. And on the right-hand side is the non-uniform height buildings. So we can see, if you look at that same sort of 17.2 height building, that's 17.2 millimeters, you can see behind it and the other buildings, which are just a little bit higher than that plane, you can see that the pollution has been sucked up in the wake behind them up to this higher level, and then is a new plume being released at height. So the occasional tall building in a neighborhood can do a good thing to air quality at street level. It can sort of scoop the air pollution up to higher levels, but it actually worsens the air quality at the top height of the building slightly. But the advantage here is that it disperses the air pollution downstream at height, which can be very beneficial. Next. So those were just a few sort of aspects of the morphology of the buildings and the way that they can affect street ventilation. But here's the question: is this a street canyon? These are very tall buildings in a neighborhood in Hong Kong. Do we understand what the flow is doing in this kind of street, or do we have to find some kind of new concept of what the flow is doing? I don't really think we understand yet how any pollution released at the base of this street would be ventilated to the air above. Next. So we can ask ourselves, what are the appropriate flow archetypes for these high-rise cities? Next. So the final scale I want to spend the rest of the talk on is urban boundary layer ventilation across the whole city. Next. So traditionally, trying to measure wind speed above a city would involve sticking some kind of an anemometer on a mast. You can't get very high, and you can't put them everywhere in a city. So this is a new technology, Doppler LiDAR, which is proving extremely useful in giving us much more information about the flow across cities. So just to give you a 101 on how they work, the physics behind them, and I'm talking about a Doppler LiDAR here, is that we have a device with a laser beam which comes out into the air above. So you look at the left-hand side, the laser beam coming out of the LiDAR. The laser beam next, it encounters some particles in the air. Next. What we see is the Doppler effect. So the frequency of the light going out, if the particles are moving upwards, then they are moving away from the laser, then the frequency of the light coming back to the LiDAR is slightly shifted to be reduced. Next. And if the particles are coming towards the laser, next, then the frequency is slightly increased. Okay, so we have a Doppler shift in the frequency, which is proportional to the velocity of the particulates that the light is bouncing off. So by this measure, we can have a quantification of the wind component in that line of the laser beam. Okay, next. So what do we get out of these instruments? So we can really see processes in the boundary layer like we've never seen before. So what you're seeing here is examples for when the laser beam is pointing directly upwards continuously. So the top graph we've got as a function of height on the y-axis and time on the x-axis, we have the aerosol backscatter, literally the intensity of the light scattered back from particles in the atmosphere. So the greener the colours, the more gunky the air. So we can see overnight there's a layer of pollution at low levels, that's around about 500 meters. And then during the daytime, as the boundary layer deepens, then those aerosol particles disperse and the air becomes cleaner. The middle panel is showing us that wind velocity component. So red is an updraft and blue is a downdraft. And we can see in the middle of the day between about 9 and 1600 hours that there is an increase in the depth of the boundary layer as these convection sort of up and down drafts get more strong. And on the bottom, we have the vertical velocity variance. This is showing us the turbulence, which is due to the convection. And we can also see coming out at night time is a little bit of turbulence, which is closer to the surface. What we can do, though, is use that turbulence to define the top of a mixing layer. Next. So what we were interested in was seeing what the difference is between the urban boundary layer and the sort of depths of that mixing between the urban boundary layer and the rural boundary layer. So what we did was an experiment over some years and months where if you look at the map, we had measurements, Doppler lidars in the middle of London and also at a rural site called Chilbolton, which is about 125 kilometers away. Just to zoom in, you can see the map of London, and zooming in again on the right-hand side, on the bottom right-hand side, you can see a close-up of the site where we had our instrumentation. Next. So the question was, how do these boundary layers evolve? Were they different? And we had a case study of 5 days where there were absolutely clear skies, which never happens in Britain. And there was a high pressure system in place. So it was pretty polluted, the winds were quite low. And what we did was to derive a mixing height from that variance data from the LiDAR and see the difference between the urban site in red and the rural site in green. Now you can see over the 5 days that the urban boundary layer is always deeper, but what's really curious is that the rural boundary layer is being suppressed and reducing in height, and the urban boundary layer is increasing. And what we think is happening over the 5 days of this quite sunny period, the urban area is getting hotter, the convection is getting stronger, the boundary layer is getting deeper, whereas in general, the high pressure system is making the atmosphere more stable. So the rural boundary layer is actually getting more and more stable. The pollution is getting trapped in a smaller layer. So you can think about the ventilation of the urban boundary layer. It's actually improving its own ventilation over a few days, whereas in the rural areas, it's really quite suppressed. Next. If we use the Doppler lidar in a scanning, by moving the laser beam across the sky in a certain scan pattern, we can get a wind profile. So if you look at the top left-hand corner, there's a little vector diagram of this. So if you point the laser upwards, then tip it to the north, then tip it to the east, you have 3 orthogonal components of the wind, which you can then combine to give you a wind vector. And you can do that at different heights that we call gate heights, so every 30 meters or so. Now, what we did in this piece of work to see if we could trust what the LiDAR was giving us was to compare the wind vector from the LiDAR with the wind vector measured by a sonic anemometer. And this was placed, if you look at the right-hand side, on top of the BT Tower in London, which is a telecoms tower, which is, our sensor is around about 190 meters height. So if you look at the graph down below, that shows us the LiDAR hourly wind speed against the BT Tower sonic anemometer wind speed. And on the average, there's really quite a good agreement between the methods. So that gave us some confidence that if we look at wind climate statistics from the LiDAR, we're getting something that we can trust. Next. So we measured wind profiles over many hours. And one of our questions was, how do measured boundary layer wind profiles compare with engineering models? So if you want to design a building, like I've got silhouette of the Shard, that's currently the tallest building in London, around about 320 meters or so, and the BT Tower for scale as well, about 200. What is the wind profile? You want to understand that because you want to understand the wind loading on the building in strong winds. So what we have here are in red the kind of wind profile models that an engineer would use to make that kind of prediction. And we have 3 different models which are commonly used. You can see one of them is labeled, is called the logarithmic wind profile, and it's the steepest red line that you can see to the left of the plot. In black are the actual average wind profiles as measured by the LiDAR for 4 different categories of winds, the different quartiles of the winds. So the low wind quartile is the bottom 25% of the data set, and the very high is the top 25th percentile of the data set. Now you can see the very high profile is very steep, and it coincides quite well with that logarithmic model, whereas the low profile is it's got a very, very different gradient. And that's the sort of information that engineers till now haven't really had. It's these kind of instruments that can measure across all wind conditions that can give us an idea of what the wind does under different stabilities. Next. So we can use this laser to measure in places we couldn't get before, if you like. So one of the things we did was to measure the evolution of winds along an urban river throughout the day and see how they vary. And this is coming back to the idea in the top right-hand diagram of urban ventilation corridors. Are we seeing a flow along the river through the city? So this is the River Thames. And this was an experiment done in collaboration with Sue Grimond when she was at King's College London. And there is a dark building just to the left-hand bank of the photo, which is where we put the instrument. Next. So looking from above, we had the instrument sitting in the building to the north of the river. And the black lines are showing us what we did with the laser. We pointed it in one direction directly across the river and then another angle slightly to the left of it, and used those 2 observations to give us 2 components of the horizontal wind vector. Now what we see on the right-hand side of the results. So next. I want you to focus on just 2 positions in the river. The blue arrow is right in the middle of the river, labeled 11. And the black arrow is on the edge of the river, labeled 4. So we can see on the right hand side, we can see the daily evolution. This is the average of many, many observations. And we can see for the big blue arrow in the middle of the river, the blue data points in the more bold color show that there's very much a strong diurnal cycle from about 3 meters per second at night to around about 5.5 meters per second in the middle of the day. Now that's in the middle of the river. At the side of the river on the black, we can see that it's a smaller range and lower wind speeds as we might expect. What's interesting though is that the lighter colours in the background are the results when we had cloudy weather. I forgot to say the bold points are when it was sunny and clear, and the lighter points are when there was cloudy weather. And you can see there's a very suppressed diurnal variation in the winds when things are cloudy. Next. And what we think is happening there is that this is a diurnal cycle of the mixing height. So as the boundary layer deepens during the day, the convection is mixing down higher momentum air at the top of the boundary layer down towards the ground, and it's increasing the wind speeds. And when you have cloudy days, that convection is not so strong, and therefore you see less of a variation of the wind speed. And just down in the bottom there, you can see the mixing height, the diurnal evolution of the mixing height in the month closest to these observations. If you look at the blue line shows you the urban mixing height variation. And you can see there is the diurnal cycle of the winds in the river correlates quite well with that, the mixing height overall. So the pattern of winds local to the river is very much influenced by the entire sort of urban surface and the cycle of stability that it goes through as the boundary layer increases in height and decreases. So those two different scales of ventilation are very much linked. Next. So the final example I want to show you is coming back to those tall buildings. We saw from earlier that they're definitely doing something potentially beneficial to pollution downstream of them. But how far downstream do tall buildings change the flow? You know, how long is the wake from one of these buildings? And this was an experiment done as part of the MAGIC project, which was from March last year to, we're still going with those observations. If you look at the photo at the bottom, that's a panorama shot showing a little white LiDAR on a rooftop close to a building labeled A, which I'll come back to. And this is an area of London where there are quite a few tall buildings that we can study the flow around them. And if you look at the photo just above, that's of a wind tunnel study that was done by Denise Hertwig et al. To look at the flow behind the same building, building A. So the LiDAR measurements, with the way we did the LiDAR measurements was to scan the LiDAR horizontally. So this is taking a horizontal slice through the wind field that we could then start to compare with the wind tunnel study. So you can see on the top left, the colored diagram is showing you some of that data from the LiDAR. So we have an example of a southwesterly wind, and you can see this building is labeled A and B. Have a look at A in particular, that's the same building. And what you're seeing is the normalized velocity deficit. It's a bit of a mouthful, but what it means is where the colors are purple, then the wind speeds are lower relatively to the spatial average, and where they're green, they're slightly faster. Okay, so the building wakes are showing up as purple on this plot. Next. Now, why might we want to measure the dimensions of these wakes? Well, what we wanted to do was to compare observations of real building wakes with what is assumed in a dispersion model. This is one called ADMS build, which is quite often used in the UK by local authorities. Next, and hit next again. Okay, so what that model is doing is trying to simplify the flow around the building, right? So it's representing the grey block is a building, and it would represent the flow around building A like this. So you have an area, a near wake area near to the building. If you look at the right-hand side, you can see this is the vertical cross section through the flow, and you can see there's the near wake is where there's a recirculating zone immediately behind the building, which lifts the pollution up, and then there's a far wake where the flow is going forward again, but it is much reduced because of the presence of the building. So we're interested in the horizontal length of the wake in red and the lateral width of the wake in blue. Next. So for that particular building, we can compare the LiDAR observations of this velocity deficit, which is the points, with the model prediction, which is the line. So we can see that the wake width is of the same order of magnitude. It doesn't, of course, capture the asymmetry of a real building wake. And on the right-hand side, we can see the wake length. So this is as a function of distance from the building in meters. And we can see that the model slightly, it's of the same order of magnitude as what we're measuring in reality. But there is a difference in the intensity of the wake. In real life, the wake is a little bit more intense by about a factor of 2. So these are the kind of observations we can do with the Doppler LiDAR, and we've done them in different stabilities, which I haven't got time to show you. And those kind of measurements can be used to help support the development of air quality models. Next. So that was a visit of a whistle-stop tour through some of the processes which are influencing ventilation, not just of individual buildings, but the streets outside the buildings and the city, the urban boundary there in which the streets and neighbourhoods sit. And we can see that some of those ventilation processes are linked across the scales. So we really need to understand wind, climate, all those scales in order to design cities that can breathe more easily. Next. So the ventilation is very much controlled by those processes at a range of scales. Some of those flow patterns can be influenced by good urban design, the shapes of the buildings and the shapes of the streets and the shapes of the city within its regional context. So that some of those natural processes can be exploited. And this is like the principle of permaculture. If any of you grow vegetables, then you take account of the context of a city or a context of growing stuff in your garden, then you will be able to design things better. The flow is highly non-linear. We saw that in some of the flow around the cubes. So the details can matter, like the shape of the buildings, but nevertheless, we should try and draw out some simple learning from these more complicated studies. And finally, the flow is always tricky to measure in real life. So, so we need various methodologies, not only field observations by Doppler lidars, which are very promising, but also wind tunnel physical modeling, and also numerical simulations. And all of these things together will help us understand wind climate and city ventilation a lot better. If you're interested, there's a couple of things at the street kind of ventilation scale. There's a new network in the UK kicking off. You can follow us and find out what we're doing. At the boundary layer scale, using these kind of new technologies, there's a cost action, a website where there should be some information coming online in the next couple of years that will help you set up these instruments and do it yourself. Okay, many thanks.
Thanks, Janet, for your presentation. So I didn't see the question in the question box. So if you have some questions, you can ask Janet directly.
There seems to be one question. Let's have a look. Sorry,
okay,
I just
we have a question from Ron. Yeah,
oh,
yeah.
I can't really see them very much. Okay, so I think I'm just trying to read some of the questions. For certain city layouts, smaller, more uniform and vertical, could strategic placement of urban lakes and concentrated high density urban forests create horizontal pressure gradients that could enhance ventilation? Or maybe the effect would be lost in the noise. I think some of these local, some of these sort of neighborhoods, I mean, that's kind of sort of a neighborhood scale intervention. If you introduce a lake or an area, then you will definitely enhance sort of ventilation local to that area, but the effect might not extend that far into the rest of the urban canopy. Slide on the diurnal cycle. Yes. So, I mean, I think it's always worth remembering that there is this invisible boundary layer going up and down above our heads, which is going to control the concentration at street level. It just depends how much it controls street level concentration, say pollution. If you had quite wide open streets, then it's going to be having more of an effect than if you have those very narrow, tall streets like you have in Hong Kong. Sorry, I'm having trouble actually viewing the questions. Can somebody help me out? Maybe somebody could read out the questions.
Yeah. There is a question from Ron Fockett from USA. Is there an optimum organization of building height to facilitate natural ventilation?
I think this is a very interesting question. There's been quite extensive work done in various, particularly in Japan and Hong Kong, looking at ventilation, particularly after the SARS epidemic in 2003, looking at different configurations of buildings and trying to find some simple design parameters that might help. I mean, what we found with that wind tunnel study was you could vary the heights of the buildings, and that was very effective at improving street level air because it improved vertical dispersion. But what we found also was that made the city more rough, so the horizontal movement of air through the city was slowed down. So I think it's bearing in mind context again. If your problem is that you want to get the stuff you're releasing at street level up out of the street, then varying heights is a good idea. If your big problem is that there's movement of air through the city and you want to maximize that, then perhaps it's not such a good idea. So I think it depends a little bit on what the context is and what you're trying to achieve.
Yeah, thank you, Janice. For there is next question. From the Matthias Steiner. I wonder whether you have any insight regarding the design of urban observing network, given this flow, very complexity of the flow in the urban area.
Yeah, I think that's a really good question. I think it is worth thinking, well, where can I actually get some measurements as high as possible, which can be reference measurements, say on top of tall buildings. I mean, some of these are just opportunistic. So the BT Tower, we just had good fortune that we could have access to the tower, and they have a very good, well-exposed position on top of that. And then that become a good reference measurement for measurements around the city that might be in slightly messier situations. You know, if you stick from what I was saying, if you stick a measurement at an intersection, that's going to be very, very difficult to interpret. If you have a measurement in a long city street, then that can give you perhaps something a little bit more consistent in terms of interpreting it. But comparing any local measurement with some kind of reference, which might be an airport measurement as well, I think that can help to interpret some of these more messier flows within the city.
Yeah, thank you. There is a question from Mukund Tewari. What's your talk about Hong Kong's building? Maybe he's mean the high-rise building. What is challenging modeling just such high-rise building like in Hong Kong?
Yeah, I mean, Hong Kong must be one of the most difficult flow situations that you have, in that you've got incredibly high buildings, you've got very steep mountains very close by, you have sea breezes which are influencing the city as well. And I think we're, of course, there's many cities sort of developing, especially across Asia, which are equally high and extensive. I think we have to do a lot more experiments with that kind of geometry. We've done a lot of experiments with very low street canyon kind of geometries, and that's been very good to develop our understanding. But I think we need to start thinking about idealized experiments with these tall buildings. Clearly, numerical simulations, there's all sorts of challenges there about getting a deep enough domain to capture the flow across a high-rise city and resolving the flow right at the bottom of those buildings. So I think that's where the state of the art lies, is trying to address those tall building canopies.
Thank you, Janet. So there's one interesting question from Shaja Ghani. How do you expect urban ventilation to the change in response to climate change?
I think that's a very interesting question, because I mean I've been talking about the wind in this relatively short talk. I mean, temperature, the change in temperature between the city and the landscape around it, that could change some of these larger ventilating flows. You know, if you have a rural area which is drying out and getting warmer compared to the city, that can change some of those larger scale flows. I think the other thing which is happening with climate change, I mean, we know that our individual buildings, they're designed for cooler climates. The actual performance of an individual building, it might ventilate quite well for a colder climate, but then as the climate warms up, then some of those ventilation properties might get worse. So we might have to think about moving to low energy mechanical ventilation to boost ventilation into the the coming climate. But I hope we can harness as much of the natural flows that are available as possible. And of course, reducing pollution would be a very good thing to do alongside climate change.
Yeah, thank you. So there is many questions actually. So maybe we cannot answer all of this. So let me select some question from this one. So the question from Kate Brewster. The horizontal flow seems more reliable at rooftop. That might argue for more use the rooftop turbine and funnel.
Right.
Yeah.
So there is such a thing as a wind catcher, which is a very old sort of architectural design. So something on rooftop that will catch the rooftop level wind and funnel it down into the building and street level. I mean, some of these vernacular architectural designs, we should probably start thinking about them again and incorporating them into modern cities. Yeah, definitely trying to harness the flow which is just above our heads would be a very good idea.
Yeah, thank you. So there is a question from the Yu Ting Kwok. He have a question. He or she have question as that you mentioned an extremely deep street canyon in a high-rise city like Hong Kong. What kind of measurement campaign would you suggest to understand the canyon wind flow in these cities?
Yeah, I mean, there are people who are already doing some measurements. I think one would have to think about the different scales. Okay, so it's measuring at street level, but attempting to measure at different heights, which might be instruments put out of buildings, or indeed these lidars are reducing in the sort of the resolution of the measurement. So if you have a deep canopy like in Hong Kong, about 100 meters high, some of the buildings, then some of these lidars can resolve the flow down to around about 20 meters, and potentially using that kind of laser-based device alongside some more traditional measurements. And I know in Hong Kong there are radiosondes as well, for example, which gives you an idea of the background state of the atmosphere. You know, it's thinking about measuring at different scales as best you can with the technology available, and always thinking about some kind of simulation alongside the observations, just to make sense of the observations.
Okay, thank you, Janice. Maybe because of time, so maybe we have a last question. So from the Peter Krang. He had a question, as many cities are trying to increase their green infrastructure, how do tree and vegetation lining the street building impact the upward ventilation?
I think that's another quite hot topic, and I was looking at some research the other day. The street, so if you have a line of trees within the street, there is some evidence that can actually inhibit some of the ventilation of pollution out to the street, out of the street to the air above. So potentially putting streets on pedestrianized, putting trees in pedestrianized areas where there is not a release of pollution beneath them, that's the best kind of urban design to do. I think we all agree that having vegetation and trees in urban areas has got many, many benefits. So we should just not put them in the wrong place.
Okay, thank you, Janice. So maybe we have to end the webinar today because of time. So again, we're so sorry to delay for 5 minutes at the beginning for some technical issue. So again, thank you, Janet, for this great presentation you give you shares today. In this presentation, I found there are many innovative and interesting ideas that would benefit not only us urban climatologists, but also a wide range of urban planner, designer. So we really appreciate your presentation. So thank you, so everyone, for joining us today. So as China told at the beginning, we have the webinar at the February next year. So hope we can see you also there. So have a great holiday season ahead, and please stay safe and healthy. Thank you.
Thank you.
Thank you, Janet. Yeah, thank you.